There we go. Okay, so we are ready to look at our final module, which is module number 8. We're going to be looking at mechanism design. So we're going to be stepping back a little bit in our textbook. So we're going to be looking at chapter 5 in our textbook. And you might feel like maybe this is a little out of order, but actually I think this is the perfect order. We've learned a lot about four-bar mechanisms, kinematics in general, all that basic stuff, velocities, accelerations, looking intimately at each one of the links. But now we're going to kind of do, if you would, reverse engineering, where we're going to look at an output motion that we want, and we're going to be then designing the mechanism that would be appropriate for it. Okay, so we're gonna be spending time on four-bar mechanisms. So I want to look at what we have here for our, first of all, our learning plan. You're going to notice here in Module 8, as I said, we're going to be working through Chapter 5 in our textbook. So that's going to be the PowerPoint that we're going to be using. I'm going to be, excuse me, populating our session recording tonight and the next time we get together in the session recordings. And then you're going to notice that we do have some practice problems to do. So there's going to be 4 practice problems. I'm anticipating we're going to get through the first 3 tonight, and then we'll save the last one for the next time that we're together. So we'll be working on these together. And then lastly, we're going to have an assignment for this. So as we take a peek at our final assignment, number 8, you're going to notice that there are 5 problems. The first 2, a little bit shorter, so they're worth 10 points. The last 3, there are 2 parts to them. So I thought I would kind of give them their own, set of points. So I don't know if you can say they're longer. They're probably a little bit more involved, but it's mostly because there's 2 parts to it. There's going to be one AutoCAD part where you're going to be laying it out, and then the other part is going to be the calculations that you're going to do. So that's what we have as far as the assignment. So I am going to start by going back up into our learning plan here. I'm going to click on our PowerPoint presentation, and I have my book opened to chapter 5. But as we get started here, kind of refreshing our minds on four-bar mechanisms, specifically, well, not really specifically, but one of the very common types that we see over and over again is a slider crank mechanism. And what I want you to do is just take a moment, because we haven't really looked at four-bar mechanisms since acceleration. Okay, so it's been a couple modules. And what I'd like you to do is just take 1 minute and generate a quick list of like practical applications of a four-bar mechanism and, slider crank mechanisms. They can be the cranker rocks, whatever, or crank rockers, whatever you want. And it can be remembering, different types of kinematic diagrams that we did, or it can be remembering or recognizing things around you. So just 1 minute to generate a short little list. Okay. I don't know if it's a minute or not. I wasn't keeping track. But again, short little list, just some ideas of just kind of recalling what they're like. And now what I want you to do is I want you to take 1 more minute and do a quick Google search, whether it's on your computer or your phone, and just what are some additional applications that you come across for four-bar mechanisms, slider crank mechanisms, those types of things. Okay. Again, not really sure if we had a minute or not, but we'll move on. And what I want you to do is just if I could have some people share what's on their list, okay? So in the room here, a couple people, what do you have listed on your 4-bar mechanism application list? A sewing machine? Yes, yes. And we did a kinematic diagram on that. And we looked at that, right? Sewing machine, excellent. Others? A what? A saw, absolutely. A reciprocating saw. Okay. And oh, I was just gonna say virtually, you guys want to put it in the chat. It looks like Christian has a baking mixer. Nice. A door opener. Sorry, I'm gonna try to get him down. Oh, a pump jack. Oh, good. Excellent. Engine piston, classic example. Absolutely. Any piston. Yep, good. I've got a hand pump. Yes, absolutely. Oh, mump, pump. What else do we got? You guys are good. Oil well pump. James?
Car suspension.
A car suspension. Yes. Air compressor. Yes. Awesome. Any others that anybody wants to share? Josh? Oh, sure. Like an automated, like a robotic arm. Yeah, for an automated. Uh, yes, 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 yes. So an automation arm. What do you want to call it? Automation arm robot thingy. Yeah. I know what you're saying. Like you kind of repeatedly like go through the motion. Yeah. Yeah. Oh, pliers, absolutely. Hand tools are classic examples. Again, absolutely. Awesome. So we've got a pretty nice list here, right? So I have a little squiggly down the middle here because now I want you to think about kinematic design. We know that we've been talking about this all term, that kinematic design is like the first initial design steps, the layout and things like that. So what I want you to just, and this can be, I'm not asking you to make a list, but I want you to just like blurt out or tell me what are considerations at that kinematic stage of the design process that you would consider in any one of these items that we see here. Like what would be things, variables that you want to be concerned about or nail down in the kinematic design part? Remember, no forces, no materials. Yep, joints. Yep, types of joints, right? We had a couple different types of joint. We had pins, we had like sliding joints. Oh, back row, Josh. Profile. What do you mean by that? Oh, yes, profile, the space needed. Absolutely. Yes, and those who are operating speed. I like it, Jack. Thank you. So operating speed. Oops, speed. And then special points of contact, yes, or special points of interest. Is that what you mean, Christian?
Yeah.
I'm thinking that's what you meant. Interest, right? Or I guess in contact too. I'll put in contact because that's what you put originally. But I think I can understand that. James, did you have one? Oh, yep, the throw angle. So something that's oscillating, what is that angle that it's going to go through? Awesome. What else? Anything else that you can think of? Go ahead. Yes, yes. So stroke, maybe, right? The range of motion of the parts. Yes. And that would be of all the different lengths, right? Anything else? So when we have like a final operation in mind, Usually it's the output motion is where we start. So for instance, what is the stroke that we want to achieve? What is the throw angle that we want to achieve? And then depending on the other elements that you talked about here, the different, space relationships that we have or how much or little space that we have is also going to start to dictate the types of mechanisms. Now, we talked about 4-bar mechanisms, but at some point you may even consider chains, belts, belts, or gears to get something done as well. Maybe you need to gear down or slow down a speed off of a motor. Maybe you just have like a generic motor and that's not the speed that you need something to be. So you might have to, use a belt drive or a chain drive or a gears to get the rotational motion where you need it to be. So all those sorts of things. So yes, and I'm so glad that not one person said material, not one person said force, right? Because we know that in the kinematic design of things, we're not concerned about that yet. That comes in strength of materials and statics and all that. So and actually dynamics, when we do dynamics next term, we're going to be taking into consideration forces and how that's going to affect the motion and such. So that's coming, but kinematic. All right, awesome. So let's go back to our PowerPoint presentation. We made our list of the variables and the considerations, and now we're going to kind of get into chapter 5. So chapter 5, what we get to do here in chapter 5 is we're going to learn how to use graphical methods to initiate the design of mechanisms. So we are going to, and this is where we're going to be using kind of a combination of hand calculations to kind of get us started, but then we're going to be utilizing AutoCAD to lay things out so that we can complete the rest of the design. Find out why it's important to know these techniques and these processes, and it helps us, we're gonna be looking at why that is. And then also start to think about your capstone course. Now, I'm not going to have you list anything out, but I want you to realize and even try to point in some areas where the things that we've learned in kinematics here, where it's the the layout phase of the design process, is something you're going to do very early on in your capstone. So things like, do I need to have something rotating? Do I have to specify a motor? That's kinematic analysis. How fast does that need to be? Or what is going to be the stroke of something that might have to have linear motion, and how am I going to accomplish that? So those are things that you may find are going to be reapplied in your capstone course. So objectives of our chapter here is, first of all, we're going to be describing mechanism synthesis. I don't know why in this particular book, but I think maybe they're trying to be fancy. Really, all it is synthesis is mechanism design. So it's just another word for design. So we're going to be looking at mechanism design. We're going to look at designing inline and offset. I should have added that in here. Slider crank mechanisms. We're going to know the desired mechanism time ratio, and you're going to understand what that means. We're not going to be using timing chart. I pulled that out this time because I felt like it wasn't a subject that was super important, but I didn't get it out of my PowerPoint here. So we are going to be skipping over this. But then we're going to be jumping down to using graphical methods to design our mechanisms and finish up the actual values that we need for each one of the dimensions. So let's start with synthesis here. Synthesis is the process of designing a mechanism that produces the desired output for a given input. Okay, normally and I'm not going to say normally, but when we start the design process, it's the output that we know the most about, and we've got to work backwards to the input. In the problems that we've been doing throughout our kinematics class, many times we're given the input, and now we've got to identify the output. So what I like about this last module in chapter 5 is that it's probably the most realistic process of how you're actually going to do this when you're out in industry. So it kind of brings everything together that we've done. Now, there's different, we end up trying to decide what is going to be the type of synthesis or the type of design that we're going to be implementing in our kinematic phase of our design. And that's where you really start looking at the particulars, like, is it going to be a slider crank mechanism? Are we going to be maybe utilizing different types of drives, belt drives, chains, gears, and such to get our rotation in the right speed and, if you would, direction. And that's what you do at that point. we're going to kind of have that identified for us. We're going to be like, this is going to be a slider crank mechanism, and then you're going to go through the process of the designing, of finishing up the design. Or it's going to be a crank rocker mechanism, and you're going to finish up the design based on the criteria. And then the other part of the design is going to be the dimensional synthesis. And this is really where now we nail down what are the lengths of the different links, because the lengths of the links are going to dictate the motion that we end up seeing. So really determining, what is that final design dimensionally. And that's where we spend the most of the time here in this particular chapter. So the first thing we're going to start talking about is time ratio. Okay. So there's going to be the first type of motion we're going to look at is called symmetric motion. And symmetric or symmetrical motion is when we have the same inward and outward motion, and it has the same amount of time that it takes to go back and forth. So it's called a kinematically balanced mechanism. So for instance, if we have a slider kink mechanism, the amount of time that it takes to go all the way to its outward stroke and back is going to be the same in both directions. So if it takes 1 second to go out, it's going to take 1 second to come back. Now, one of the nice things about this type of a mechanism is that you can do work in both directions. So if you have a saw, for instance, and it has the ability of not only cutting in one direction, but the blade has the ability to cut back in the opposite direction, then this type of motion is advantageous because now you can actually do work in both directions rather than just in one. So engine mechanisms are symmetrical, windshield wipers are symmetrical. So I wanted to show a quick video of a symmetrical motion. Full screen. So you'll notice here as we see this slider go in and out, just by observation, you can see that as it goes out, it's the same amount of time to go out as it does to come back in. The other thing about this, I'm going to stop it right here for a second. The center of rotation of our crank, if we extend that, it is in line with the path of the slider, okay? That is always going to be the case when we have a symmetric layout, okay? The output path is going to be in line with the crank center, okay? It's just kind of looking at a top view, back side. Yeah. Okay. So that's to the end. I know it's kind of a weird looking guy. All right. So that's symmetrical motion. All right. Then there's non-symmetrical motion. And this is going to be where there's a difference between the outbound stroke and the inbound stroke as far as time. Many times these are called quick return types of mechanisms. So that on the outbound longer stroke or the stroke that takes more time, the work is going to be done. But then on the inbound stroke, part of the stroke, it's going to actually speed up. And so you can save time because you're not going to do work on that inbound part so you can get back into position to then go out again. So things like cutting machines, packaging, moving machines or devices are really designed for this. So let's look at this one. So here's the slider. You're going to notice that when it comes back to the left, it's going slower, and then it speeds up when it goes back to the right. So coming to the left, this would be the work cycle, if you would. It would be the slower time. And then going back, same distance, but it's going back faster, would be the quick return side. All right, that's it. Okay. Now, there are going to be some equations that we are going to use to kind of prepare us for the layout work that we're going to do in AutoCAD. And we see some of these listed here. So what we're going to do is, the book has these spaced out. So I always think, and you know that I like creating a nice little equation sheet. So we're going to start with the equations that are actually at the bottom of page 109. And I'm going to go underneath and we're going to make a mechanism design equation sheet, if you would. And again, this is chapter 5. Okay. Now, where we're going to start here is on page 109, we have section 5.2. This is time ratio. And at the bottom here, they start the series of equations that we're going to be looking at. So the first one that we see here, this is called time ratio, and the variable we use is going to be Q. Okay. So we're going to start out, our first equation is going to be Q. Okay. And the equation, now they have it written out in word form, is going to be, we're going to say T1 over T2. Okay. So Q is going to equal T1 divided by or over T2. And this value is going to be either greater than or equal to 1. Okay. Now, when Q is equal to 1, that's going to be symmetric motion. Okay. And inline, I'm just going to put inline, like a inline slider crank. Okay. When Q is greater than 1, this is going to be non-symmetrical. It's going to be SYM. And it's going to be an offset slider crank mechanism. Okay, that means that the crank center line is going to be offset from the path of the slider. Okay. So over on the right-hand side then, we're going to say Q is equal to, and it's called the time ratio. There are no units because we would have, like, for instance, seconds over seconds. They would cancel out. It's just a ratio. It's just going to be a number. T1 is going to be the time in seconds of the slower stroke. Okay. So it's going to be how much time it takes out, like on that work part of the cycle. And that's going to be in units of seconds. T2 is going to be the time of the faster stroke. And that's also going to be in seconds. So if time 1 and time 2 are the same, okay, it's going to be, the same number divided by each other. It's going to be 1. And that's when we have that same amount of time going out, same amount of time coming in, symmetrical. But when it gets greater, so when our slower time is on top, more time on top divided by less time on the bottom, that's when we're going to get this value of greater than 1. Okay. And that's going to be the offset type of a design. Now, another variable that we're going to, or another way that we can calculate or determine Q is going to be equation 5.2. Okay, and that's right below. So I took Q, and instead of doing time of the slower stroke, we called that T1, and then T2 was the time of the quicker or the faster stroke. Now we're gonna use this equation right here. We're gonna write this one down. 5.2, Q is equal to 180 degrees plus beta over 180 minus beta. So 180 degrees plus beta divided by 180 degrees minus beta. Okay. Beta is the imbalance angle. And that's going to be in degrees. Sometimes beta will be given. Okay. Sometimes it'll be given, but sometimes we got to also calculate it. So by rearranging that equation above, they just showed it in another form down here, solving for beta. So I like having that one available as well. So beta is equal to 180 degrees times Q minus 1 on top, sorry. Minus 1 on top divided by Q plus 1 on the bottom. Okay. And again, the imbalance angle is only going to, okay, how can I say it? Beta is equal to 0 when we have an inline or a symmetrical. And then beta is going to be equal to an actual value when we have an offset or a non-symmetrical. Okay. We're going to turn the page then. Okay, so these were the three that were at the bottom of page 109. And then at the top of page 110, there's two more. We've got delta T cycle. So this is the total time of a cycle or one revolution. Okay, so delta T cycle is going to be equal to T1 plus T2. Okay, it's each one of those sides of the stroke. So delta T cycle is going to be the total time of one revolution or one cycle, they call it. And then the last equation that we have is going to be the one on the top here, 5, and this is the rotational speed of the crank. Okay, a lot of times this is going to be referred to as W2, just like we always have. Okay, they have it identified as crank there, and the way that they show it is kind of weird. It's correct, but they have it's the reciprocal of, so 1 over delta time, but I'm gonna show you a better way to write it, I think. So we're gonna do W, and I'm gonna put CR for crank. It's gonna be equal to 1 revolution divided by the total time for one cycle. That's what it is. Okay. Many times this total time is going to be in seconds, but we're going to want to report it, as we know, in RPM. So W crank is going to be equal to the rotational speed of the crank. And it's always going to be in RPMs. In this particular chapter, there is no converting to radians per second or anything like that. This will always be in RPMs. Okay. All right. So that's going to be kind of like our main equations that we're going to be kind of going back to. And then we're going to have different conditions depending on the type of mechanism that we're looking at. Okay. So just to kind of get our feet wet with this introduction to the items that we see here, we've got our first example problem, and this is going to be our first practice problem as well. This is on page 110, example 5.1. We have a quick return mechanism. All right. They don't have any sort of a illustration here. So they're just giving us a description. We have a quick return mechanism is to be designed where the outward stroke must consume 1.2 seconds and the return stroke 0.8 seconds. Determine the time ratio, the imbalance angle, the cycle time, and the speed at which the mechanism should be driven. Okay, so we'll kind of look here and identify what we know and what we have to find. Okay, so I'm going to keep my mechanism equation sheet kind of handy. And this is going to be example 5-1 or 5.1. And what I know is I know T1 is equal to, remember T1, if we look back over here, T1 is the time of the slower stroke. So it said that we were doing a quick return mechanism. So that means that it's going to have a slower stroke on the outbound, and then it's going to come back more quickly, right? And then it's going to have a slower stroke again and then come back quickly. So it says that the outward stroke is going to consume 1.2 seconds And then the return stroke is going to be 0.8. So the larger of those two is going to be our T1. So our T1 is going to be 1.2 seconds. And our T2 is going to be 0.8 seconds. Okay. That's all we're given. That's all we're given in this problem. Okay. And what we're going to need to find, okay, we're going to need to find, they want us to find the time ratio. So if we go back to our equation sheet, the time ratio is Q, okay? It's going to be the variable Q. So we need to find Q, right? We also need to find the imbalance angle. We look back at our equation sheet. The imbalance angle is beta, okay? So we need to find beta. We also need to find the cycle time, okay? So the total time of one revolution is going to be that delta T cycle, okay? So we need to find that. And then we need to find the mechanism or the speed at which the mechanism needs to be driven. So that's going to be our W of our crank, okay? Our angular velocity or rotational speed of our crank. So those four things that we need to find for this problem. All right. So since we need to find, I'm just going to kind of start at the top here. Since we need to find Q, let's look at our equation sheet. You're going to notice our very first equation that we started with right here. Q is equal to T1 over T2. And we have T1 and T2. So step number one is going to be Q is equal to T1 divided by T2. And that's going to be 1.2 seconds divided by 0.8 seconds. And our Q, what do we get for that value? All of our calculators out. It's more fun. What is it? 1.5, James Scott. Did anybody else get that number? Yep. Seconds cancel out here, so there's no units. 1.5 is Q. Okay. So that's our first one done. Great. The next one is going to be the imbalance angle, which is beta. Okay. So if we look here, you'll notice that we have an equation. Beta is equal to, it's our only one, right? 180 degrees times Q minus 1 over Q plus 1. And we just calculated Q. So it looks like that's going to be a good equation to use. So beta is going to be equal to 180 degrees times Q minus 1, Q plus 1. So 180 degrees times 1.5 minus 1, 1.5 plus 1. What do we get for beta? What is it? 36 degrees? Anybody else get that? Yep. Well, 36 degrees. I'm going to pull up the chat again. Just in case anybody, feel free to add for those who are virtual as well. And make sure that you're getting these same values. Okay, so 36 degrees. Now remember, when there's beta, all right, when there's an actual value for beta, that means that we're going to have an offset slider crank mechanism. Okay. And in this case, they said that it was a quick return, so it has to be offset. If it being a quick return, that means that my outbound and my inbound strokes are not the same time. It is not going to be an inline slider crank. It has to be an offset. Okay. And because I have a value for beta, tells me that as well. All right. Then the next thing, we need to know what the total cycle time is. Oops, so step number 3. Total cycle time is going to be T1 plus T2. Okay, and we have that equation on our equation sheet. It's just adding the outbound and the inbound times for each one of those strokes. So we know that to be 1.2 seconds plus 0.8 seconds. So our total cycle time is going to be 2 seconds, right? Be easy to add those two together. We're going to need a calculator. All right. And then the last one that we have is going to be the rotational speed of the driver, okay? So step number 4 is going to be W crank. It's going to be equal to, so if we go back to our equation sheet, 1 revolution, which is 1 cycle, divided by the total time to do that 1 cycle, okay? So 1 revolution on top divided by the change in T cycle, okay? So 1 revolution stays on top divided by 2 seconds. Now, this is going to be in revolutions per second. We would have a half a revolution per second, right? But we know that we always report our rotational speed in RPMs. So we want to change this from revolutions per second to revolutions per minute. So we're going to multiply by 60 over 1 minute. Okay. Seconds cancel here. And what do we get for the rotational speed in RPMs? 30. Yep. 30 RPMs. Yep. Excellent. So those are going to be very typical equations that we're going to be, or the work that we're going to do, Q's and betas and times. There's going to be some other, little relationships that we have depending on the type of mechanism that we use. So there'll be a couple more that we look at, but this is going to be kind of like the side work that you do before you would create the layout in AutoCAD. Okay. All right. Questions. Kind of, like I said, kind of warming us up to the vocabulary as well as the relationships here, and then kind of working through that. Okay, so that's our first practice problem. Let's go back to our PowerPoint presentation. So we did example 5.1. Now we're going to look at designing the slider crank mechanism. There's 2 different types of slider crank mechanism. There's going to be an inline and there's going to be an offset, okay? The first one we're going to look at here is going to be an inline. Inline means, as we stated earlier, that the crank center of rotation is in line with the path of our slider, okay? In line. All right, so we see that in both of these cases here. So if we look at an engine piston, for instance, I'm going to do a Control, click. This is going to be, again, our classic example of an inline slider crank mechanism. The crank here is going to be the camshaft. Connecting rod goes up to the piston, and the piston is going to have that linear or slider motion, okay? Then if we look at a sewing machine, sewing machines, hacksaws, compressors, they're another example. So if we look at this one, same type. And this one.
Great. The new GoDaddy Arrow has AI marketing tools to help small businesses easily.
Going to be another example of a slider crank, but this time the center of rotation is offset from the slider. So we end up getting a quick return mechanism in this case. It's a little bit more involved, but when we see the operation in just a second. So that inline slider mechanism, we're going to look at an example of that. That's going to be on the top of page. And again, not unfamiliar to us at all. The top of page 114. And we are going to look at figure 5.3. Okay. I'm going to zoom in here. And what I want to do is just kind of review some of the labels that we see here. If you remember on a kinematic diagram, we have labels for each one of our links, okay? The first link we have is going to be the frame, all right? So you'll notice that as number 1 with a circle around it. Number 2 is going to be the input link or the crank of this 4-bar mechanism. So that's going to be number 2. It's going to be connected here. This is going to be the center of rotation. Link number 3 is going to be the connecting rod that is going to connect the crank to the slider. Slider is number 4, okay? Now joints each have a letter. The first joint, which is going to be at the center of rotation, is going to be joint A. Joint B is going to be at the end of our connecting rod. I'm sorry, the end of our crank. Joint C is going to be at the center of the slider. And we don't see D on here. I wish they would have put D here because it's not consistent with what we normally would do. We would have one extra joint in here that would be joint D. Now they don't show it because it doesn't end up being part of the design, if you would, but there is a joint there constraining it to be in linear motion only. Okay, so technically there's another joint there. So 4-bar mechanism, 1, 2, 3, and 4 is our slider. Now, the way that we see this mechanism right now, with the solid lines here, this is just a random position inside of its path, okay? But where we see C2 and C1, these are going to be the extreme positions of the furthest out point, which is C2, which is the center of that slider, and C1 is going to be the closest point. Now, the difference between those two is called the stroke, okay? Stroke is always going to be based on the linear distance that, in this case, the slider is going to actually move through its full motion. So one cycle is going to be all the way out and all the way back in. Okay, all the way out, all the way back in. So the stroke is that displacement that we see on that slider. And again, most often that is going to be the output, if you would, of our mechanism. Okay, so the input is going to be the driver over here, which is going to be our crank, and then our output is going to be how far is this going to go back and forth? What is the stroke? All right. Again, familiar terms to us, familiar terms to us. Now, as we look at this section and we look at inline slider crank mechanisms, there are going to be two relationships that we see. The first one is going to be, how do we determine the length of our crank? Okay, L2. So this is going to be, L2 is going to refer to the length of the actual crank right here. All right, so how long does that need to be? So if we know what our stroke is, we just divide the stroke by 2, and that's going to be the length of our crank. Okay, and it makes sense because if we look, when the crank is horizontal here in line with the path of our slider, okay, and it's laid out, that's going to be the furthest that it's going to go. Then, as this is the center of rotation, when it comes back around over here, it's going to pull it all the way back. So if we look, that distance between B1 and B2 here is the diameter, if you would, of the circle that the crank makes. So half of that is going to be the length of our crank. And that is going to be half of what the stroke would actually be. Does that make sense to everybody? Do you see that? All right. So the L2 is really easy, if you would, to determine once we know the stroke or if we know the stroke. So on our equation sheet, this is only for inline. Yes. So what we're going to do is we're going to create a little section here for the relationships for an inline slider crank. So I'm going to put in inline slider crank. Okay. And this is going to be referring to figure 5.3. Okay. And we know that L2 is going to be equal to the stroke divided by 2. They use delta capital R for the stroke. I don't know why. I don't like it. So I always write out stroke. It's just their variable. Okay. So this again is going to be the crank length. Okay. is going to be L2. So it's the length of link number 2. And again, using the convention that we learned early on, 2 is going to be that input crank. The other relationship is going to be the length of the connecting rod, link number 3, okay? L3 is going to be equal to 3 times the length of the crank, or L2. So this is going to be the connecting rod length. Okay. Now, when we have an inline slider crank, this is when we have symmetric motion. We know that Q is equal to 1, okay? And beta is equal to 0, or we don't calculate a beta, okay? And we'll learn about a beta in just a little bit. So just know that beta is equal to 0. We don't calculate a beta for that. So these are kind of the things that we keep in mind with an inline slider crank. All right. So let's look at our first inline slider crank problem, which is going to mimic one of your homework problems. Okay. So I don't know why, but the book did not do any examples inside of the chapter for the different types of mechanism problems. So what I did was I picked at the end of our chapter where we have our problems listed on page 120, we're going to do example or a problem number 511. This is going to be our practice problem. And this is going to be very similar but different numbers to your homework assignment problem, which is 512. Okay, so we'll go through 11 together and you can use it as the guide that you would do, or the process for the next problem, which is going to be your homework problem. So as we look here, the instructions are directly above for this section of problems here. So it says for problems 511 through 518, design a slider crank mechanism with the time ratio Q, stroke delta R4, and the time per cycle of T. So in here, they kind of broke their little rule. So they had inside of the chapter, they're referring to the total cycle time as delta T cycle. But here in this problem, they're calling out the time per cycle as just T, okay? So when we look at number 11 here, Q is 1. Our stroke, delta R, is going to be 2 inches. And T, which is the total cycle time, is going to be 1.2 seconds, okay? So I'm going to start my problem here. And we're going to say, okay, problem 5-11, okay? And we are given Q is equal to 1. Q is equal to 1. Our stroke is equal to 2 inches. And our delta T cycle, so the total cycle time, is going to be 1.2 seconds. Okay. What we need to find here, okay, so for each one of these problems, it says we need to specify the link lengths L2, L3, and offset distance L1, and the crank speed, okay? So essentially, we want to find L1, L2, L3, and W2. And it's W of the crank, which is link number 2. Now let's talk about L1. Okay, L1. Now we haven't, if we look up in our figure 5.3, which is an inline crank, you're going to notice there is no L1 because on an inline, there isn't, all right? The L1 is going to come into play, and we're going to just take a sneak peek when we have an offset slider crank. The L1 is the offset distance between the center of rotation and the path of the slider, okay? So right away, because this is an inline, and I shouldn't really say it inline right away, but because the Q is 1, remember that's symmetric, and it means it's an inline, and all down here as well, we said Q is 1. So since we have a Q1, we can say then, number 1, L1 is equal to 0. This is an inline, there's no offset. This is going to be an inline slider crank. Okay, so there's no offset. L1 is going to be equal to 0. But because of that same thing, we can say beta is also going to be equal to 0, right? As we said, beta is equal to 0. Now, what is beta? We also haven't looked at that. Let's take a sneak peek again at beta. So when we have this offset slider crank mechanism, it's going to be the angle created between the AC1 when we have our slider all the way in, our slider all the way out. It's this angle between those two. That's what that is. It's called the imbalance angle. All right. Because we have an inline slider crank, when we're in the outboard position and the inboard position, there's no angle between those because they're in line with one another. That's why beta is 0. Okay. So when we know, first of all, when Q is 1, we know that it's going to be an inline slider crank, which means that there's no offset and there's no imbalance angle. There's no beta. So we know those right away. Step number 2, before we get into the lengths of the other one, I always like to do my W2 first because otherwise I forget it. And I through all the whole problem, I do the whole design, and then I'm like, oh, I forgot to do the W. So let's go ahead and do our rotational speed of our crank, or link number 2. If we go back to our equation sheet, it's going to be 1 revolution over the total time cycle. Okay, so 1 revolution over delta T cycle. All right. So 1 revolution divided by, and we're given here, the total time for 1 revolution, 1 cycle is 1.2 seconds. Okay. Now this is going to be in revolutions per second. When we report our W2, we need it in revolutions per minute. So we're going to say 60 seconds in 1 minute. Do that conversion. So our W2, what do we get? 60 divided by 1.2, is that 50 RPMs, right? Awesome. Looks like we've got agreement in the room. Okay, 50 RPMs. So we'll be done with that. So the only 2 that we have left are L2 and L3. Okay. So if we go down to that little section that we just created just now, the inline slider crank section, L2 is going to be half of the stroke. All right, we know what the stroke is. Okay. So we're going to go up here. Stroke is 2. So step number 2, L2 is going to be equal to stroke divided by 2. So 2 inches divided by 2, it looks like L2 is going to be equal to 1 inch, right? Oops, sorry. So that means I've got L2 done. So all I have left is L3. And we also had a relationship for that. L3 is 3 times the length of L2. Number 4, L3 equals 3 times L2, which is 3 times 1 inch. So L3 is going to be 3 inches. Okay. Now, for an inline slider crank, this is all we need to now go ahead and draw it. So now you're going to draw the kinematic diagram that we just identified here. Okay. So I'm going to go over to AutoCAD. All right. And this is an inch increments. So what I'm going to do is I'm going to talk this through first. Okay. And then I am going to turn it over to you guys so that you can make the diagram. Okay. I don't want you to have to rush through it. So I want to show you what I have here. So first of all, this is kind of like, in kind of a random spot around the crank revolution. This is going to be our 4-bar mechanism. So we've got our frame, our crank, connecting rod, and then we have the slider. Notice that we have all the standard labels. 1 is the frame, 2 is the connecting rod, 2 is the crank, 3 is our connecting rod, and 4 is going to be our slider. Then we have the letters at each one of the joints, starting with A, where's the center of rotation for our crank, B is at the end of the crank, beginning of our connecting rod, and C is going to be at the center of our slider. I did add D here because that is then going to be the last joint that we have. Even though it's not going to be part of the design, it's good to put it on there, okay? Now, what I did for this problem, and this is really where the design starts. We knew that our stroke was 2 inches. So I drew this in 2 phases, if you would. I didn't want to go over the top because I thought it was a little bit cluttered to look at. So what I did is in the diagram above here, I have this in the most leftward position for the stroke. So this is what we're calling C1, okay? And if we go straight down here, then as we extend our crank in line with the connecting rod, the furthest out position is going to be C2. So if we look at the dimension between C1 and C2, that is our 2-inch stroke. Do you see that? Okay. And then I do have these orthographically projected, if you would, in line with one another, top to bottom are A. So then in this position, we have horizontally the crank, which is 1 inch. Horizontally in line with it is going to be the connecting rod, which is 3 inches. And then, like I said, I kind of had a dimension from the 2 inches for the actual stroke. Okay. So this would be, if you would, the 3 positions of this mechanism. Okay. So what I want you to do is I want you to take some time to create this and make sure that you have a good handle of how to do it. Now, this is very similar to what we did in the past, except what you've done now is you've identified based on these criteria at the beginning, you've now designed or determined what those lengths should be. And now you're creating the kinematic diagram to match that. Okay. So I'm gonna kind of focus in on these 2 parts right here. And I'm going to let you finish this up because this is going to be the screenshot that's going to accompany the manual calculations that we just did. Okay, so once you have the diagram all set, and the 2 most important parts are going to be these bottom 2, if you would. The top one is just kind of like so that you can see, you know, what if you would, a standard, you know, or a in a random spot. What the inline would look like. Okay, so you would take a screenshot of the portion of the AutoCAD drawing, and then what you're going to do is you're going to then scan or take a picture of the manual work that you do. So as we saw here, using the input information, we calculated each one of these lengths, and then using the L2 and the L3, we showed the inline slider crank mechanism in its 2 extreme positions so that we could show the stroke as well as the length of each one of those links. Okay. So that's, I would say, the easiest one of the 3 that we're going to be doing. Now what we're going to do is we're going to take it a step further, and we are going to do now an offset slider crank mechanism. Okay. So I'm going to go back to our PowerPoint presentation. And we did the inline. We're now going to look at the offset. The offset is going to be figure 5.5 on page 115. Okay, on page 115. Now, we're going to start by looking at the illustration right at the top here. Okay, so the obvious difference here is that we now have a distance between the center and the path that that slider takes. So this is going to be our offset. So our L1 dimension here now is going to be part of the equation. Additionally, we are going to have a Q that's going to be greater than 1 because our outbound stroke, the slower side, is going to be a larger number in time than what our quick return is going to be. So our Q now is going to be greater than 1. Additionally, we are going to have an imbalance angle. The imbalance angle is going to be the difference between the distance from point A down to the closest position of our slider to from the furthest position of our slider, and it's the angle that's created between those two lines. Okay, so that's going to be our imbalance angle. So those three elements now are really going to be the difference from the previous one. So it's a little bit more, if you would, involved as far as a couple extra things that we have to consider. So what we're going to do is we're going to add to our equation sheet. And we are going to create another section, but this time it's going to be for offset slider crank. Okay. And this is going to be always referring to figure 5.5. Okay. Now, as we've already pointed out, L1, that dimension, is going to be our offset. Okay. And that is going to be determined by CAD. All right. So I'll show you how we're going to get that offset distance. Okay. Now we're going to find that L1 is going to be a value less than L3 minus L2. But we're going to see how we actually generate this in CAD, but that's going to be something that is going to be a relationship. We're also going to find the distance for L2, which is going to be the length of the crank. We're going to take the length of line AC2 and we're going to divide that by 4. AC2 and divide by 4. Now, what is that? A is going to be the center of the crank rotation. So from that point A all the way to the furthest outbound slider position, that's C2. So the length of this line, AC2, divided by 4 is going to be the length of our crank. And we know that because we also know the same relationship is going to hold too, where L3 is going to be equal to 3 times L2. Okay, so if we look at AC2, this length right here, this is when we have the crank in line and stretched all the way out with the connecting rod. If the connecting rod is 3 times L2, and then we've got L2, that means that there's 4 L2s along that length, right? Yeah. So once we get this laid out and we find that intersection, we're going to measure the length of that AC2, and then we're going to divide it by 4, and that's going to be our L2. Okay. And then the leftover is going to be the L3. All right. Now, we already know that Q is going to be greater than 1. All right. And we'll get that. I believe it's going to be given in our problems that we look at. Okay. We also know that beta is going to equal a number. So we're going to be calculating a beta. There's going to be a number there. It's not going to be 0. Okay. Now, to use beta, we're going to have to look at a little bit more construction here. Okay. And we'll also do this. I'm going to show you this in CAD. I'll demonstrate it for you. So if we look from, this illustration here down to here, okay, this is C1, this is C2, and this is point A. All right. So this is before like the rest of the details, if you would, are in there. So when we look here, zoom way in, we know that the angle between AC1 and AC2 is beta, that angle right there. And we know how to calculate that. We have an equation for that. That's our imbalance angle. But when we construct this, we're going to need a place to start, okay? And that place to start is actually theta m. This theta m is not going to be a calculated value. This is going to be a specified value. And sometimes in the beginning, you're like, I don't know where to start. I'm going to tell you to start between 30 and 50 degrees, okay? Between 30 and 50 degrees is going to be an angle. And you're just going to pick one, all right? When we do our problem, the next problem that we do for this type of an offset slider crank mechanism, we're going to pick 45 degrees. But anywhere between 30 and 50 degrees is a good place to start, okay? So that's going to be a specified value. And then our n value, our theta n here, is going to be how we're going to get our C2 in place. So as we look at the geometry there, and I'm going to, again, referring to this figure, our theta n is going to be equal to theta m minus theta b. And that, or minus beta, sorry, minus beta. Okay. And whatever we calculate for beta is going to go down there. Remember, m is going to be specified, okay, by designer. And the problem is not going to give us that value. So you're going to find, when I'll talk it through, when we need to use that theta m, I'm going to say, I'm picking that number. All right. So make sure that you have that as a note, because it's not going to be in a problem for you. And I don't want you to get to that point like, I can't construct this because I don't have theta m. And I'm going to be like, do you remember what we said in class? And you're going to say, no. I'm going to say, but I had you write it down. So, so this is going to be something that we're just going to assume. Okay. All right. So those are the relationships for the offset slider crank mechanism. Okay. All right. So let's go ahead and look at an offset slider crank mechanism problem that we'll do for our practice problem that'll also relate to one of your homework problems. Okay. So the problem that we're going to look at is going to be 5, I think it's 15. Yes. So going back to page 120 in that very same section we were in earlier, this time we're going to scooch down to problem 515. Problem 515 is right here, and it is going to be similar in nature process-wise to 516, which is going to be your homework problem. Okay, so we're going to do 515. So just like the earlier problem, our givens are going to be our Q, our stroke, and our total time. So we're going to write those down. Our Q for this problem is 1.37, right? 37. Our stroke, 46 millimeters. And our change in time cycle, so our total cycle time is 3.4 seconds. We need to find, okay, W2, L1, L3, and L2. Okay. Yes. Omega. When we get to that step, I'll kind of talk you through that. Yeah. But what they're asking us to find, the problem is asking us to do these. So along the way, we might have some other things that we calculate, but so James's question was, do we need to put the omegas and the betas in here? They're going to be along the way when we do some calculations to be able to lay it out. But as far as what the problem wants us to find, it's these 4 things. What didn't we put in our previous problem?
They put it into the.
Oh, we don't have to. Yeah, that's not the, oh, I'm sorry. I thought you meant, so our rotational speed, you don't have to show it. No, no. You don't have to show that in AutoCAD. That's just a calculation that we do. Okay, so we can get started. So we'll start with calculating the rotational speed. So our step number 1 is going to be W2. It's going to be equal to, if you need to go back to the equation sheet, this is going to be the rotational speed is 1 revolution over the total time of 1 cycle. So 1 revolution over delta T cycle, which we are given right there. Okay, and that's going to be 1 revolution over 3.4 seconds. And I want to report that in RPM. So it's going to be 60 seconds on top, 1 minute on the bottom. Seconds cancel. And my W2, what do we get for the rotational speed and RPMs? Yep, 17.6. I got 4.7, but 6.5 is fine. Yep, RPMs. There we go. So W2, done. Okay. Now, L1, we just go back to that illustration where we saw the construction, okay? L1 is going to be the offset from the center of rotation down to the path of our stroke, okay? The path of our slider. That is going to be constructed using these 3 angles right here, okay? Because it's an intersection of those 2 lines from those 2 points. So we can't calculate an L1. We're going to measure it once we construct, okay? So that's going to come from CAD. So we really do need to calculate our beta, specify a theta M, and then calculate our theta N, okay? So we're going to start with our beta. So step number 2 is going to be our beta. Now, we've got our equation for beta is going to be 180 is equal to, or I'm sorry, 180 times Q minus 1 over Q plus 1. Should get 28.1 degrees. James has a thumbs up. Awesome. Good. Lex's thumbs up. Great. Josh is nodding. And Isaac is nodding. Thank you. All right. So now, as I said earlier, this is the part where this is not going to be a given value. Okay. So we're going to calculate that theta N is equal to theta M minus beta. Beta is going to go there. Okay. But remember, this M, I'm just specifying. Okay. So for this problem, as I kind of said earlier, I'm just going to specify 45 degrees. Okay. Again, starting anywhere between about 30 and 50, good place to start. And minus beta, which is going to be my 28.1 degrees. Okay. So my theta N should come out to be 16.9 degrees. Okay. So this number and this number, remember, this is specified by designer. Okay. All right. Now we have what we need to start constructing this in AutoCAD. All right. So I'm going to go over to AutoCAD. I have it kind of started already. So we'll do that kind of that same process. I'm going to kind of talk you through. I'm going to show you what I've got here. So right now. So if you would just kind of watch what I'm going to do here, because I'm going to give you time to kind of lay this out, but I want to show you the process and the numbers that we used here. Okay. So I'm going to use the center line first, or no, I'm going to use hit it first. Okay. Because I'm going to be on my C1. So I am first going to draw a horizontal line from the center of C1, and I'm just going to make it horizontal. All right. You don't, it should snap along here. I just want it to be a random length. Okay. This angle that I'm going to rotate is going to be my M, my theta M. So I'm going to do a rotate. I'm going to select my line. The center point is going to be the center. Make sure you get the right center here, right there. And now I'm going to rotate it. I have to rotate it from where it was at in a clockwise direction. So this is going to be negative 45 degrees, negative 45. So remember, this is that theta 1 that you could put, like I said, negative, you could put 30, 40, whatever it might be. Okay. Place to start. 45 is a good place to start. Now what I'm going to do is for the other one through C2, I'm going to put my object line. I'm going to do another line, same thing from that center. And I'm just going to go horizontal, nice and long, so that I know I'm going to intersect with my other line that I just created. And I'm going to rotate again. Okay. Let's see. Rotate this one from the center of C2 here. And this is going to be the negative, and this is going to be theta n that we just calculated, 16.9. Sure it's in there correctly, 16.9. Enter. Let's see. Negative 16.9. Enter. There we go. Now I've got an intersection. That is where my A is. That is where A goes. So I can't calculate that. I can't calculate L1. So now I'm going to move center here to the intersection. Okay, that's going to be the center of rotation. All right. And now if I go to the dimension layer and I do a linear dimension, my L1 is going to go from this center to the path. So 20.1 will be the number that you should get. If you use the same 45 degrees, which you should for this practice problem, make sure you use the same numbers. Okay. That's going to be my L1. So if I do a copy here, and you do want to label this because this is one of the things that you're using CAD to equals. Oh, goodness sakes. There we go. That is the dimension that L1 is. All right. So now if I go back underneath, I can say step number 4, L1 is equal to 20.1 inches. And I got that from CAD. Okay. Okay. That's how we got it. We didn't calculate it. We generated it based on those angles. So I'm going to let you catch up with this and make sure you get the L1 equal to 20.1. Okay, so now we're ready to kind of go on to the next step. Okay, so if we go back underneath, we know that our L1 is that. Now we can do L2. Okay, if you recall, relationship that we have. Oh, Lex. Oh, oh, you're right. Thank you. This is all millimeters. Yeah, just out of habit. Thank you. I appreciate you catching that. Yeah. Thank you. Okay, 20.1 or 20.075 millimeters. So now we're going to find our L2. L2 we know is going to be AC2 divided by 4. So this is going to be AC2 divided by 4. Now, the AC2 we're going to measure off of our diagram. So we're going to go back to AutoCAD, okay? The distance from A, the center of A here, to C2. So this is going to be an aligned dimension. I'm going to go from from the center here to the center down there. Okay. And I got 69.058. Okay, 69.058. You should have something very close to that, if not exactly that. So I'm going to go back underneath here, and this is going to be 69.058 millimeters. And this was measured from CAD, We're going to divide that by 4, and that's going to be my L2. What do we get? Oh, no, not divided by 2. I said divided by 2, but it's divided by 4. There we go. So 17.265 millimeters. Okay. All right. So now that's going to be our crank. So I'm going to draw a circle. I'm going to keep it on the dimension layer. That's fine. I'm going to draw a circle, and the center is going to be the center of A, and the radius is going to be 17.265. Okay. And now at the intersection here, this is going to be the joint for point B. Center to the intersection. So this is going to be point B, but this is going to be B2. Okay, because that's going to be the furthest position out along B. Okay. Does that make sense to everybody? What was that? Let me put it on here. An aligned dimension. So for L2, from here, oh, did I grab? I didn't grab the right spot. Hold on. Center from here to there. 17.265. Okay. Now my white line, I can trim back to here, here, and then I'm going to come in, and it is going to stop at the center. So that's going to be the length of link 2. And I'll add the link designations in a little bit. I'm just putting the points right now. Okay. Now the other one that we have is going to be along the green line. Okay. So this is going to be I'm going to trim back along here. Then I'm going to copy my B2 and that same joint from this center to the intersection here. And this is going to be B1. Oops. And then I can get rid of that circle. And then if I do another aligned dimension from the center of where B2 is to C2, this is going to be then the length of link 3 is 51.793. So we should be able to, we go back underneath here. L3 is going to be 3 times L2. Okay. So if we do that, it's going to be 3 times 17.265 millimeters. And L3, this is going to be No, 51.795 millimeters. And if we go back underneath here, I got 50. How come I got 0.95? How come I got 0.93? Oh, I think I know why. I know why. This is probably rounded a little bit from that overall length, so that's why it's a little bit different. So that's okay. I bet you if I would pull this out 4 and 5 decimal places, we would have numbers. All right. So now what I'm going to do is I'm going to show you over here, and I'll let you finish up this diagram. These are the elements that you need to include in your diagram. So you're going to notice that we have L1, L2, L3, each one of those labeled, the overall, okay? And then you're going to also notice that you're going to have beta. You don't have to label beta. I just want to see the 28.1, 16.9, and the 45 degrees. Okay. So you want to just add those couple of extra things to the diagram that you see here. So I'll add these in as well. CLP1. So we're going to be putting, this is an L2. This will be an L3. 2 equals L3 equals, and then we're going to add the angles. So this would be your theta n. Imbalance angle there. And then our 45-degree angle. There you go. And that should do it. I'll let you guys finish that up. I'll pause for a little bit and then we'll resume in a little bit. Okay, so once you have your diagram all set and you have the labels that we see here, this is then going to be the screenshot that is going to accompany the practice problem 515. So you're going to include both the manual work that we went through, identifying each one of the elements. So remember, it wants you to do W2, which we did right away in here in step 1. And then it wants L1, 2, and 3. So down here, L1 we got off of CAD after we did our angles, okay? L2, we also got that off of CAD. And then L3 was derived from that as well, okay? Now, when you have L1, L2, and L3, I want to make sure that you label those in your diagram. So you'll notice that L1 is over on the left here, the distance between the crank center of rotation to the path of the slider. L2 is the length of the crank, and L3 is going to be the length of the connecting rod, okay? Then you'll also notice the 3 angles. I didn't label them beta, theta, M, and theta N, but I did dimension each one of them. So the 16.9 for the theta N, the 28.1 for the beta, and then the 45 for the theta M. Okay, make sure that those are labeled. And then ultimately the stroke too, because that's really where we started everything. Okay, so once you have those 2 things done, then that's going to be what you submit for problem number 515 in the practice problems. Now, this is as far as we're going to go content-wise this evening, but you would be prepared to get most of the homework started, okay? So what I wanted to do was to go to the back of the, or to the end of the chapter where the problems are and just kind of go over what you are going to be, doing for homework. Okay. So on page 120, the first 2 problems that you have here are going to be calculating QB and rotational speed of your crank, okay, for number 5.2 here. And this is similar to example 5.1. 5.4, I'm going to tell you, this one's a bit of a challenge problem. I'm going to say one thing. And some of you who have me for statics, most of you have, Two equations, two unknowns. Keep that in mind. All right. That's going to be, it's going to be used in this problem. Okay. So, I'm not going to go into that just yet, but just know that if you're like, I don't feel like I have everything, two equations, two unknowns. All right. I'm going to say that. So that'll be useful in 5-4. Then the last three problems you have are 512. 512 is going to be just like 511 that we did for our practice problems, but different numbers. Okay. This one's going to be an inline slider crank. Okay. As far as what you hand in, it's going to be the manual work with the same calculations that we did for 511, and it will be the same format for your diagram that I showed you in that problem as well for the AutoCAD. Okay, so you'll need both hand calculations and AutoCAD. This is one of the 20-point problems. The other one that you can do is going to be 516, which is going to be similar to 515 that we just got done doing. And again, same calculations, hand calculations that you'll hand in, as well as the AutoCAD work and labels that we just looked at. This is also another 20-point problem. Again, I'm kind of considering 20 points for the manual work as well as 20 points for the CAD work. Okay. And then the last problem that we have, we will go over the practice problem, which is going to be 19, which will then mimic what you're going to be doing for 520. And we'll save that for the next time that we're together. So like I said, the majority of what you have for your homework, you already can start working on, and then we will finish up the next time that we're together. And then you'll have the rest of the time this evening to work. Okay. So I'm going to ask first, are there any questions at the moment? Okay. If not, I'm going to stop the recording and I'll let you guys work independently.